Okay, good evening. Welcome again. We just talked about the exam, some logistics, and new posts are there on e-learning. Go check them. You'll get, inshallah, a response on your design project proposals by the end of the week, inshallah. Meanwhile, in today's class, we should finish chapter 4 of the book. So we're done with this part. We started talking about interfacing parallel ports, parallel I/O ports last time, and interfacing with them with some devices. We're going to continue this part today. Do a class demo in C, use C together to do something, then start with chapter 6. This is chapter 6 about interrupts. So last time, I'm sharing, right?
Yes.
طيب. Last time we started talking about parallel I/O port. What does a parallel I/O port mean? How to configure a port as an input port or an output port. We saw the ports, digital ports and analog ports. What is the difference? What do we mean? What is the default when we say a parallel I/O port? We saw how to interface with LEDs, how to compute the current limiting resistor, multiple LEDs, 8 for example, putting them in some arrangement to do a 7-segment display. Okay, and we stopped here last time. And I was talking before we ended the last class lecture that this common cathode, so these LEDs, this means that all the LEDs over here have a cathode, okay, that is common. Okay, this is the common cathode. Now, when I write a 1 here, this means that I connected this to VCC here on this pin. There will be a current that would flow from the higher voltage to the lower voltage and thus turn on the LED. But what happens if I pull this to high, to VCC? There will be no voltage drop and no current. The LED will turn off, right? So I was saying, if you don't want to take this common cathode directly to ground, you can take it to another pin, for example, port H0, and you can connect it to ground, by writing a 0. This will enable the 7-segment, all the 8 LEDs over here. If I connect it to, if I write a 1, then I'm connecting it to high, then high and high here, no voltage drop, the LEDs will not turn on. So I disable all of the 7-segment display. And this leads us, of course, and we talked about if I want to show the number 2, for example, here, the shape of number 2, I need to do this 1, 2, 3, 4, 1, 2, 3, 4. These are ports. 6 is A, right? 6 is A, so port B6. So port B 0, 1, 2, 3, 4, 5, 6, 7, and 0 to 7. These are port B7. Here the connection, if I directly connect 6 to G, or it depends. So if A is connected to 6 and B is connected to 5, then the connection here, A, so A will be, this is A, right? 6, this is A, B, C, D, E, F, G. Then what LED I want to turn on, I write a 1, so the A will be a 1, the B will be a 1, the C will be a 0, the G will be a 1, the D will be a 0, and so on. Okay, then you get your number. And this number, to show the shape of number 2, will be different than if I connected these in a different way, in a different order, right? So port B0 to 6, A to G, in this case, if I'm using in my if I'm using in the menu in our Dragon 12 board, this is the older version of the board where we had a common cathode, and we had port H used to interface the 7-segment display. So I had port H 0, 1, 2, 3, 4, 5, 6, 7, port H 0, 1, 2, 3, 4, 5, 6, 7 connected to bits to 7-segment display, segment A, B, C, D, E, F, G, H, and if I wanted to show the number 4, for example, so 4, this is A, B, C, D, E, F, G, A, B, C, D, E, F, G. So 4 will be turning on these LEDs, right? So F is a 1, B is a 1, G is a 1, and C is a 1. Everything else is 0. So the number we have here is 66, right? 0x, 0x, which is hexadecimal 66, right? And here it is, 66. This is true when this was a common cathode, which means a 1 turns on an LED, a 1. If we are using a common anode, we need to flip all the bits, right? So this will be a 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. This would result in 0x, 9, 9. 0x is hexadecimal again, right? So it will be the opposite, which is 99 is the one's complement of 66, right? One's complement. Okay, so to show the number 5, I'll have to display 6D on port H. To show the number 0, I need to write 3F on the on port H, and so on. When we use multi... Yes, Mustafa.
بالنسبه لترتيب خلينا نحكي الموست significant والليست بالنسبه A من A to G او من G
this
to A.
This is the most common way to connect them. A to 0, B to 1, and so on.
Okay.
But at the end of the day, if I get a 7-segment display here standalone, you're free to go connect it to any pin you want. But in that case, but this is almost the convention. Everybody does this.
تمام. Okay.
So in case of multi 7-segment display, imagine I have 3 displays or 5 or 4, like this case, 5 displays. If I need to connect each one of these to a different parallel port, I'll need 5 ports, 5 times 8, 5 ports times 8 pins or 8 bits. That is 40 pins. We used all our ports to display the 7 segments. Okay, so this is not the common way to do it. We usually connect the 7-segment to one port. Let's say here in port B. Okay, port B. So you connect port B0 to A of this one, and A of the second segment, 7-segment, and the third, and the fourth, and the fifth. So when you write a 1, ideally, if the cathode is taken to ground, all of these will turn on. Okay, but if I was to control the cathode and use it as an enable for the 7-segment display, I can take the common cathode of the first one to port P, for example, 0, the common cathode of the second one to another pin, the common cathode of the third one to another pin, and so on. So in this case, if I want to show the number 23 on 2 7-segment displays, I can connect this to ground, which means I enable it, right? And connect this to high, so it is disabled. Yani high on 1. So if you write a 1 and a 1, the LED will not turn on. So the whole 7-segment display is turned off. So if I write the code of 2, which is in this case the 5B, right? If I write it here, 5B on this port, المفروض يعني what should happen if these 2 pins are connected to ground and this is a common cathode, you will see what? If I write a 2, you'll see 22. But if I enable this and disable this and write a 2, you'll see a 2 here. Then, real quick, in terms of milliseconds, you enable this other one and disable the first one and send the 3, you see the 3 here on the enabled one. Do the switching really fast, enable this, disable this, enable this, disable this, keep switching the enable in every مثلا 200 milliseconds, 300 milliseconds, or 100 milliseconds. Something really fast that your eye cannot see the switching. And when you switch, when you enable this, write the 2, write العشرات. When you enable this, write the 1, الأحاد. Okay? Then go back, enable this, write the 2, then enable this, write the 3. Do this really fast. You'll see a 23 solid in front of your eyes as if you're not switching. This is called persistence of vision because your eye cannot recognize this really fast switching. And this is the same analogy, right? When you use AC electricity to turn on a light, right? A light bulb, it turns on and off 50 times, 60 times in a second. Your eye will not be able to see it. Okay. So I believe most of you, I don't know, somewhere you dealt with this thing, but I had to cover it. Any questions here about multi-7-segment display? If you don't understand anything, please ask. Okay. Example طبعا. The digital ports, you can use them for many purposes to actuate devices, whatever. I'm coming to devices. I added if you downloaded the slides a few days ago, I updated them. Okay. But before, and here they're talking, or the book is talking about generating digital waveform using an I/O pin. If I ask you to generate a 1 kilohertz square waveform on the using the HCS12, what will you do? You can go to any port B, port B0, 1, or whatever, write a 1, write a 0, write a 1, write a 0, do some delay, write a 0, and say port B. Let me go here. Right, you can do port B كله. First, define port B DDRB as an output. Now I said you're going to start writing C. So DDRB is 1s. So output. Then write to port B مثلا 0x. All of them, all the pins, FF, all bits in port B, the 8 bits are 1s. Do some delay مثلا 1 millisecond. Then do port B equals 0, all the bits, then delay 1 millisecond. Then do this forever. This part, put it in a while one loop forever. What will happen here? All bits of port B, port B0 for example, on the HCS12 will show a 1 for 1 millisecond, a 0 for 1 millisecond, a 1 for 1 millisecond, a 0 for 1 millisecond, and so on, right? A digital wave form. This is 1 millisecond. This is 1 millisecond. So what is the frequency here? From a rising edge to a rising edge, the time would be 2 milliseconds. 2 milliseconds. So the frequency will be 1 over 2 over 2 milliseconds equals 0.5, right? kilohertz. Yani 500 hertz, right? So if I ask you to generate a digital waveform on any of the pins with a different frequency, all what you do is to compute the time and write ones and zeros with delays between them. Now the delay here is a waste of time. How do we do it in a different way using interrupts? We'll come into this next in chapter 6. Okay. This is about digital waveforms. Well, if you want more, مثلا, a sawtooth waveform, a sinusoidal signal waveform. Well, this is your job to add the interfaces, right? مثلا, if you want something, and if you add a capacitor after this pin, مثلا, the capacitor will take time to charge, right? When you have a zero, the drop will drop faster, rise, drop, rise, drop, right? You can add some filters, you can, and it is what you work here, you can reshape the waveform you get. طيب, this is a code for writing a 1 kilohertz waveform in assembly. In this case, for a 1 kilohertz, you need to change the 1 millisecond delay to become 500 0.5 millisecond or 500 microsecond. طيب. So far, we looked at how to interface with LEDs, right? We looked at how to interface with an LED because, and we connected the LED directly with the pin, like port B0, for example, because we were able to draw 10 milliamp current, for example, and it was safe for the controller to provide this amount of current and the voltage of 5 volts, right? That was okay. But what if I need something else, like a DC motor, like the example we did in the class a while ago when we actuated a DC motor. Remember, right? When I used this DC motor, how did I connect it? If you remember, we used a switch. I used this switch, an nMOS switch or transistor, right? And the data sheet of this transistor is available on the e-learning. What I did is I got the HCS12 here, microcontroller, got the signal from a port pin 0. Now I wasn't able to connect it directly, the motor directly, because I cannot give it the current it wants. This needs a 9-volt battery, 9-volt power source, higher current. This can give only 5 volts, low current. So I cannot connect it directly. I had to use an interface. So I took this bit to control the gate of a transistor, a PMOS or nMOS transistor, right? And I put the motor over here. One side of it connected to the drain, the other part to the external voltage source, which was, in my case, a 9-volt battery. So 9-volt battery. So I took the positive part here and the negative part of the battery to the source, and the microcontroller has a ground pin, and we have to have the same reference. So the voltage drop over here between the gate and source has to be has to have this. This has a reference different than the reference of the voltage you write on the pin port. So you go and take this and connect it to ground, common ground. In this case, the microcontroller just switched on or off the switch, making an N channel to be created or disappear, right? When you write a 1 or a 0, to allow the current to go through or stop. And by changing this pulse width, we were able to change the motor speed. You remember this example? You can go back in the recording. I had it even running. I still have the circuit connected here. So one way to interface with devices is to use a simple switch like an nMOS transistor. If it was a PMOS, an nMOS here will allow in an nMOS, a 0 will turn off the motor, a 1 will turn it on. If it was a PMOS, the opposite will happen, right? A 0 will turn it on and a 1 will turn it off. طيب, what else can we do? So speaking about the motor, let me use my board. And I'm sure, I'm not sure actually. So if this is the microcontroller, and I took a pin here, port B0, for example, and I connected my motor here like this, DC motor. Well, over there in the slide, I draw a simple drawing to make you understand how we connect. But this is the circuit. I don't have, this is a 9-volt source, and this is the ground, and it is common with this ground, right? This is what we did. Tamam. Now, what is a DC motor at the end of the day? The current going, this is an nMOS, right? A 0 or a 1, a 0 or a 1 will cause this to start, turn on and off, the current to flow through the motor or not. Now, remember, this motor is what? At the end of the day, you can model it as an inductor, right? The inductor, and if I am to draw it again here, this is the inductor, and this is the voltage source. This is the ground. When you write a 0, 1, 0, 1, 0, 1, 0, 1, and switch here very fast, مثلا every I don't know, 1 millisecond or 5 millisecond, 1 millisecond high, 1 millisecond low, and so on. This is a 50% duty cycle, right? That will cause the motor, if it is a motor, to run in its half speed. However, you're switching, you're causing the current to flow here for 1 millisecond, stop for 1 millisecond, flow for 1 millisecond, and so on. What will this cause?
acceleration يمكن او في تغيير variation
Yeah, you're going to cause variation in the flow of the current, right? And when we talk about an inductor, what is the voltage that is created? Well, the basic of an inductor, of the voltage across an inductor is what? L di over dt, right? Di over dt is the change in current, right, in a time unit. So if I am switching really fast, this dt goes to close to 0, switching 500 milliseconds on, 500 milliseconds off, okay. Then if you make it smaller, on 100, off, 100, on, 1, on. If this goes, the switching becomes really fast, and this approaches 0. This will approach what? Will go to infinity, which will cause the voltage to go to a very high voltage, right? Close to infinity. We can talk about a spike voltage here that is in the range of kilovolts. Okay. This would cause, why would this happen? It will happen because the characteristics of an inductor, if a current is flowing in the steady state, then you switch off, the current will try to create a voltage across itself to make a new current flow in the opposite of the original current to save it, because, right, the current is flowing this way, right? If you stop, the feature of the inductor is that it saves currents, right? Yani opposed to the capacitor, it saves voltage. So it will cause a very high voltage across the inductor to make a current flow in the opposite way to try to equalize it. This amount of voltage that will be created will be very high voltage that goes close to infinity, because we're switching the current on and off really fast. dt is approaching 0. This could cause the burn of the motor. It could cause the burn of the switch, right? So a very high voltage is created here. Usually, if you see, and in some circuits, they go have a diode connected across the inductor or the motor. Well, this could be an inductor if you want to generate high voltages, right? Usually, we use a diode. They call it a freewheeling diode, or a flyback diode. This is to cause the current to go through this path, okay, to protect, okay. And I had a few, the amount of how fast this voltage can rise to without freewheeling is up to kilovolts here. If you use a freewheeling diode, this will drop hundreds of times, okay, and the voltage will go disappear faster. طيب, what is better? What is better? To connect the motor this way, or to connect it this any parallel port, or connect it this way. Well, what will cause this current to start running? If this is an nMOS, what do I have to write on the gate here to make the current run? So everything is nMOS. Writing a 1 here, right, will create the N channel and cause the current to flow and turn on. A 0 will turn off the motor, right? What about this configuration? 0, there will be no N channel here, so no path for the current to go this way. The current will flow this way, right? When a 0 is written. So usually the motor is normally on without you having to write anything. If you want to stop it, you write a 1, you create the N channel, and the current will flow this way, right? And the resistor is to protect against short circuit. So a 1 will stop the motor, a 0 will turn it on. What is better? Well, it depends on your application, right? If your motor almost all the time is on, and sometimes you need to turn it off, well, it saves you power and energy to write a 1 sometimes, and all of the time you're 0, right? While the opposite is correct. If the motor is usually off, so you're usually writing a 0, and sometimes you need to turn it on, you write a 1. And this applies to any other actuator, of course. طيب. If it's a PWM, it will not matter, right? You're always on and off real quick. طيب. متابعين معي انتوا صح؟
Yes.
Okay. Usually these nMOS transistors, and if I show you the data sheet, it's there on e-learning, but to look at it, there are power nMOS. The one I used with you last time is a power nMOS. It has, this is it, the IRF 734. It's called the IRF 734. Okay. This is it. This can take up to voltage source, drain to source voltage, 450 volts, gate to source, plus minus 20. So very capable, powerful transistor, but it is a power nMOS, okay? Normal nMOS usually are less, but this is a power nMOS, the switching speed, and okay. طيب. So the voltage here is also limited, and the switching is fast though, because it is a solid state, right? So semiconductor. Sometimes, what if you want to turn on and off something that needs, مثلا هذا, okay, we'll take the 9 volts, 12 volts, 24 volts. What if I want something to switch something that needs different power source that a transistor cannot take? So you have the option to use a relay. We talk about relays. So a transistor is a choice. An electromechanical relay, something like, look, I try to find you pictures that people have around here in the market. A mechanical relay. A mechanical relay is what? See the sheets on e-learning? Did I put the data sheets for this one? Well, I did this last week. I think they are there. Yes. Let me look at them real quick. The relay, you know what? Yeah, I did. They are on e-learning. So if you go to resources here, I added the relay. This is the nMOS transistor datasheet. This is the mechanical relay datasheet, and it shows how it works. Okay, so this mechanical relay usually has 3 pins. 3 pins. It looks like this is it. This is the actual same one. So you have the control part. You see my mouse, right? Ground is ground, N and VCC. So you take this ground to your controller ground, because the message you'll take it from the microcontroller, right? And the ground of the power, and the ground of the power source of the device, of the power source powering your device. Let's say the device is I don't know, a big motor that you need to turn on and off, a fan or something. This, you see the numbers over here. It can take up to 250 volts AC with 10 amps, 10 ampere. Okay, so you connect the power source for the device you want to power here to these pins for VCC and ground. And over here, you get the signal from the microcontroller. This pin is the ground. If I say I want to use port B0 مثلا, port B0 will be connected to this pin or this pin. What decides, we'll look at it soon. And the ground coming from there goes here, ماشي. The ground goes here. The two pins over here, this one, normal close, normal open, are normal close, normal open. So if you use this pin, you connect your controller here. You see my mouse, right? If you connect your pin here, and this is normally closed. And usually the circuit is closed. Usually the circuit is closed. If you want to open it, yani disconnect, you write a 1. Like what if the other way around, normally open, it is disconnected, the circuit is disconnected. If you want to close it and turn on the appliance, you write a 1. It's up to you to use the normally close or normally open based on the what you want to do. And these are the voltage applied to the other device, the device you want to control. This is one sample, yani, relay. There are a lot of different relays. The other sample relay I wanted to show you, but this is again a mechanical relay. Yani, if I am to explain it for a little guy, I'll tell him, oh, okay, if you get a nail, turn on a solenoid around it, and you apply a voltage here, right? This will become a magnet, right? Magnet. You can use it to switch something on and or off, right? And this would be a circuit for, I don't know, for a motor or whatever with its own power source. And you use this magnet. If you write a 1, and this is the ground, this is port B0, you write a 1 here, right? Then you cause a magnet field to be created, and the switch to be closed, and thus close the circuit to turn on the motor. The guys who have to leave for their exam can leave. You can watch the last 10 minutes in the recording. I'm almost done. Okay, so it's a mechanical relay. The problem with mechanical relays, this is mechanical. A switch has to open and close. There is a limit in switching speed. Okay, switching speed. So you cannot apply a PWM signal on this motor here in terms of milliseconds on and off. The mechanical switching will not respond to these fast switching speeds, okay? So if you want to do, so we usually use these mechanical relays. We call this a mechanical or electromechanical relay to switch things on and off, okay? But if you want higher speeds of switching, there is something called solid state relays. Here, this is a sample, and also the data sheet is over there on e-learning. A solid state relay that can take AC. So here, these are the control pins. These are the pins that you can use to switch on and off. So yeah, you have a fan, an AC fan, مروحة. Okay, المروحة, it has a plug, right? The positive and negative that you take from your power outlet. So how to connect it? This is the power outlet. Take the negative part, connect it. The positive part, connect it here, and take a wire then to the positive. And here, you take this to port B0, for example, and this to the ground of the microcontroller. Whenever you write a 1 here, a switch here internally will close and cause the circuit to close and turn on the fan. If you write a 0, it will disconnect and the fan will turn off. And you can do the switching really fast to do a PWM. Okay, this is called the solid state relay, to be used with very fast switching. And the data sheet of such relays is on e-learning. All okay, guys? So if you are to control your fan at home, or something that needs a big memory, a big power source, other than something like this of 9 volts or 24 volts or whatever, you need to use a relay. ماشي. طيب. If no questions, I'm moving. Sample actuators. I thought to show you some sample actuators, although it's not part of any a DC motor. We used the DC motor last time. This is called a brushed DC motor, and I provided some links to show you some animation how these things. But these are a brushed DC motor, just like the one we saw last time here in my. If you see my camera, there are faster motors that are called brushless DC motors. A brushed DC motor has two lines, right? Two lines to provide the power. A brushless has three wires, and there is a brushless DC motor controller. It usually comes with a controller. How does it work? There are no brushes inside to internally reverse the voltage. Here the brushes reverse the voltage, right, to keep the magnets working. Here, this is done electronically through a brushless DC motor controller. A stepper motor that does a lot of steps. This is used for precise angle motion. A DC motor, you can just give it a command to turn on, even a brushless, right? On or off, it will keep going, and you can control the speed. But if I want a motor to turn to a certain angle and stay there, or be able, while it's running or turning, be able to know how far did it turn, the omega, the angle it turned. You can know that because this is controlled in a different way. It has multi-wires. If these are 4 wires, for example, to start you need to write a for loop, for example, and write a 1 0 0 0. This will make the motor turn a step. What is the step size? Depends on the characteristics of the motor. To move another step, you write a 0 1 0 0. Another step, you write a 0 0 1 0. So you keep moving the 1, and then you go back again. Okay, and this order is important, and you do it. For example, if you move the 1 across the 4 lines and put it a loop, maybe you will have to repeat the operation 50 times for a full rotation. Okay, to keep going, you need to keep repeating the thing in your code. This is very important. These are usually, if you hold this in your hand, and for example, a DC motor, I can turn it, right? It's easy. These are very hard, okay? They have strong magnets inside, and they're very helpful to show to controlling position, okay? Linear solenoid. This is something like the on-off. A magnet inside, you apply voltage here, 1 0. The magnet will cause this to be pulled inside. So if it's connected to a door, for example, it will be pulled inside. The door will be able to open, right? You remove the voltage, it will go back outside and stop the motor, the door. You can use it for any application you can think of. Also, a solenoid valve, a solenoid to go down or up, to close, to act as a valve, to allow air or water or fluid to pass through or not pass. A servo motor. We're going to use a servo motor in one of the demos in the coming ahead. I have some here. A servo motor is actually a system. It's a smart motor. It's not inside. It has a motor with gears and potentiometer that can measure how far you went and stop. A DC motor, if you see the number of wires here are 3, right? Ground, PWM, and power. So here you provide the PWM signal. The PWM signal will give a command to this how far this, the angle of this motor to turn. Usually the pulse width or the period, the period of a signal that you need to provide to from your microcontroller to a servo motor is 20 milliseconds. This is almost a de facto now, 20 milliseconds. And they come with different sizes, from very tiny. If you go to the lab at university, we have this big servo motors, very big ones that can you can use to rotate a solar panel, for example. 20 milliseconds, and the pulse width here usually is between 0.9 milliseconds to something close to 2.1 milliseconds, depends on the servo motor. So 2.1 will be 180 degrees. If it's a 180-degree servo motor, this will be extreme right, 180. 0.9 will be extreme left, 0 degrees. Okay. مثلا, if you want it in the middle, you give it 1 millisecond pulse width. It will go point to the middle. So it points, it controls the position. Some of the servo motors are called 360 servo motors. 360 servo motors. These are rotate 360, keep rotating. Okay. So in this case, the same thing, 20 milliseconds, but the pulse width here will control the direction. So usually in the middle, you stop. Anything, let's say 1 millisecond, you stop. 1 millisecond to 2 milliseconds, you rotate clockwise. Anything below 1 millisecond, or let's say 1.5 millisecond, you go rotate counterclockwise. The further you go from the center towards the end, you start moving faster. Okay. Interfacing with switches, dip switches are almost the same like switches, push buttons. A push button, how do we interface a push button? If this is the microcontroller unit, this is a pin, port B0, for example. I need to configure it as an input port. I put my button. Okay, let me go here. This is the MCU. I configure a port to be input. I get my push button. How do I connect it? Did you check the schematic last time? Momani asked about this. Where's the schematic? Let me show you. Of the Dragon for the switch 1 and switch 2. Did you guys see it or not yet?
نزل to ground دكتور. على ground مش
هذا هو. Let me rotate it بس for a second. Rotate clockwise one more time. And again, these data sheets are available on e-learning. So where is the push button? Here.
اليمين دكتور. أيوه.
Here. See my mouse? So they are connected to port M7 and M6 to switch push buttons. They are on the board. You see them here on the board next to the potentiometer. If you see my camera, 1, 2, 1 and 2. Okay. So in this case, see, you cannot use them this way as is. When the button is not pressed, your pin is floating. So what is the voltage you're going to read? You don't know. Okay. So what we do is we connect here a pull-up resistor to high. So on the controller here, you go find port M7, 6 and 7, and connect a resistor from this pin to the VCC pin. This is how you solve it. And this is what we do here. So you go take a resistor. This is connected to ground. This is the case we saw in the schematic. You go bring a resistor, connect it to the port and to the voltage source. 5 volts. Something between 1K to 10K will do it. For the resistor. So whenever the button is not pressed, the voltage here is going to be high, right? You're going to read a 1. When the button is pressed, the voltage, the short circuit is when the button is pressed, yes, you're connected to ground here, so you read a 0, right? And the resistor is to protect against the short circuit here. Is there another way to connect it? We can do this kind of connection different a little. A pull down resistor instead of a pull up. Right? So the normal, if the button is not pressed in this case, they will read a 0. When you press the button, you will read a 1. Okay? For dip switches, For dip switches, it's almost the same. A dip switch is connect to ground or to VCC with through a pull-up resistor. Okay, that's it. I'm done here. Last two slides, I'm going to go through them. It's about debugging subroutines because the chapter covered subroutine. Sometimes if you do a program, some debugging tips, okay, and you use subroutines or functions in C, and your program gets stuck somewhere and no response, then that means that the program counter is repeating something stuck in an infinite loop, and it's so busy it cannot respond to you what you're asking for. Okay, so how to debug such programs? How do you solve the programs? You need to go to your code, and first thing you go search for the jump to subroutine and branch to subroutine to check the subroutine. And in the subroutine, you make sure that everything inside the code of the subroutine in the stack, everything you push to the stack, you pulled it after and everything you push, you have to pull out before the return from the subroutine. Because if you push something in the stack and you did not pull it, your return will return you to a wrong address. This is a very common problem. It will make the program go to a place, the unpredictable location that you don't know about. Okay. And if a subroutine calls a subroutine and calls a subroutine, start from the leaf subroutines. Start from the leaf. They call them the leaf subroutines. Start from the end. A subroutine A calls subroutine B, calls subroutine C. Start from C. Make sure that everything you push to the stack, you pull it out before the return. Then go to the one before it, and so on. Okay. Some tips. So we're done with chapter 4. I was planning to write with you some simple program, for those who have do you all have a class?
Yes, Doctor.
Do you want me to record something or do it next time with you? Something to... I wanted to do something and see with you guys. Maybe the beginning of next class, no problem. Okay, I'll do it next time. We'll write some C code to get familiar with C and how to use it with our microcontroller, and start with interrupts. Thank you very much. See you Wednesday. If you have any question, you may stay until I stop recording.